So we don't care what the fixed points are. We just want to know how many does it have. And if we know how many fixed points an automorphism has, obviously we can decide whether it's fixed point free or not. And so that's the basis of this algorithm. And we'll go through more details later on. This is just a roadmap. And so we need to have some preliminaries because most people aren't used to working with what's called Dirac notation. And so I'm going to give you a brief intro to get you up to speed so that you can understand the notation that we work with. So first of all, I've got to talk about how we represent information. So classically, for a classical computer, information is stored as series, as a string of zeros or ones. And so either your bit, your classical bit, has state 0 or it has state 1. And those are your only two options. Now when you pass to the world of quantum mechanics, those are not your only two options. So now you have this analog, which is called a quantum bit, or qubit for short. And that quantum bit doesn't necessarily have to take on only the state 0 or only the state 1. It can take on some linear combination of these two states. And so you could view this qubit as a vector whose state lies in a two-dimensional Hilbert space. So now a Hilbert space is just a vector space over the complex values. It has a complex valued inner product. And so if you have n bits or n qubits, the state of those n qubits can be expressed as a vector in a space of dimension 2 to the n. And so here we go with this Dirac notation. I wanted to title this Sweet Dreams, Peggy. As soon as she sees this, she falls fast asleep. But I figured I'd be a little more proper than that. So the elements of the Hilbert space, they're called ket vectors, state kets, or simply kets. So here's our notation. And so what this is just representing is a column vector. So here we have a two-dimensional one, and here is our column vector. And that's all it's representing. It's just shorthand. So now we also have the dual of the vector space. So we have the homomorphisms that map the Hilbert space into the complex numbers. And so the elements of the dual, they're called bra vectors, state bras, or simply bras, and they're represented this way. So here's an example. And so if we want to write it, as you can probably guess, this is going to be our row vector. So they're just shorthand notation. We're in a vector space. We're able to have row vectors, column vectors. And so as I mentioned earlier, our qubits are going to exist in this continuum of states between 0 and 1. And when we say continuum, we give it a fancy name. We can say superposition instead of saying linear combination. And so here's an example of a state. And so here we have our column vectors, 0 and 1. And so now 0 and 1 are going to be orthonormal, working always with an orthonormal basis. So all of our computations, we're going to set them up in such a way that we start off with an orthonormal basis and we work from there. And so here we have our 0, and here we have our 1. And so if you want to represent a state in the system, then you can write it this way. Here's our linear combination. And since it's orthonormal, of course you want to have that the alpha 0 and the alpha 1, the amplitudes of those, they sum to 1. And so in order to perform a computation, you need to be able to have a register. And so let's just write it down this way. It's a little bit easier. So let's talk register. So suppose we have 2 qubits. And so when we have 2 qubits, we can represent all of the values between 0 and 2 to the n, and in this case, n is 2, minus 1. So we have, and I'm going to use the Arabic symbol, 0, 1, 2, 3. And we usually write this in terms of binary. So when we write it out, suppose we want to see what this state would be, and we're working in a 2-qubit system instead. We can write a state this way. We can say that we have, remember, a normalizing factor here. And then here, what we're going to do is we're going to have the value 0 through 3. Either way, 1, 0. And this is written in binary. Right? You could either write 0, 1, 2, 3, or you can write it in binary. And so now, we could also have a different interpretation of this. When you see something like this, 0, 0, you could also view this as a product. So if you're working in a 2-qubit system, you can think of it as starting out in this state. And then we're going to work with it, and we're going to create our superposition. So this is just shorthand. Sometimes you see it with a comma. Again, this is just notation. So that's what this is here. So when I write system, we have amplitudes, and we have all the basis vectors. So here we have an orthonormal basis, and so a state, we can write it as this combination of our orthonormal basis vectors. And as I mentioned earlier, the size of our state space is exponential in the size of the system. Well, this is what I mean, that we go from 0 to 2 to the power n, where n is your number of qubits. Okay, so quickly, let's run through. So we have a register. We know how to set it up. It can work with n many qubits. So now how do we operate on that? So we have to have the idea of logic gates. Just like for a classical computer or classical computation, you have logic gates, you have an analog, you have quantum logic gates. Now remember, we're working in a vector space, so it makes sense that our logic gates be matrices, and sometimes we call them operators. Either way, it's interchangeable. Now you have two ways of viewing these logic gates. Either you can view them as matrices, or you can write them using our nice Dirac notation, which is our shorthand notation. And so the action of your matrix or your operator can be found using this very simple rule, which is the Kronecker delta. And we'll go through an example. So for example, here's a gate. We have its matrix form. Here's our NOT gate. And so in Dirac notation, this is what it would look like. And so if we want to see a quick example, let's look at the action of the NOT gate on our state 0. And let's use the Dirac notation. We'll use that Kronecker delta rule. So it's going to be 0, 1, plus 1, 0, operating on the state 0. And so we distribute. Remedial math class would love this. I should put this on the exam. For extra credit. Forget polynomials. All right, so what's disappearing? You tell me. If we're using our Kronecker delta rule, what gets killed?
I know the answer, but I won't say.
Stephen.
Go ahead.
Well, here, these are not the same, right? So kill it. These are the same. That's going to become 1. And so our NOT gate transforms the state 0 to the state 1. And this is how we operate. And so this is a very basic example, but later on, our operators are going to be expressed two ways, either as matrices or in Dirac notation. And when we operate with them in Dirac notation, they work exactly like this. Very simple rule of the Kronecker delta.
I'd like to just add something to that, because
Yes.
I've been playing with these things lately.
Uh-huh.
So when you act on 0, you're actually taking the matrix and multiplying it by the column vector 1, 0.
Yeah.
So when you multiply the matrix by 1, 0, you get 0, 1, which is exactly the state that she wrote. So it's pretty cool how it works. You got to play around with it a little bit.
It's super cool. It sure beats
Well, it gives
doing
you-
matrix multiplication.